Okay, we're good.
Okay, so Gavin and I are back to talk about the next few chapters from Dawkins. This material covers chapters 5, 6, and 7. Is that right? Yeah.
Yes. Yep.
Okay, so we wanted to sort of make a few comments about the chapters so far. Let me first thank Gavin for filling in last week. I appreciate it. We've had sort of a medical situation in our family, but things are getting resolved. Gavin did a great job. And again, I think, from your perspective, the student's perspective, these discussions are intended to sort of, expand on the material, to sort of find the key issues and sort of main messages from each one of these chapters. I mean, our goal is not to sort of reread everything for you to listen to. I mean, we presume you guys have been reading. We presume you've been watching the videos, and I'll get to those in just a second. Our goal really is to try to hone in, to try to zero in on the main points of these chapters. I mean, we appreciate that, this book it's equal parts philosophy, biology, psychology, anthropology. It's a very wide-ranging book, which in some ways is typical for evolutionary science. But we do appreciate that, some of this material is going to be new for many of you. And so our job is to make sure that we highlight what is crucial, what is, foundational to extract out of these chapters. It is important that you read them. You will find that, those of you who do the reading will do better on the final exam. You will get more of the material. You will understand more of the material. Just pushing through it. I mean, if there are places where you get bogged down a little bit, that's fine. Those are perfect places to those are perfect issues to ask questions about. In general, the questions, your discussion seems that you're engaged, but we do want to remind you to take the time to write questions, to submit questions, discussion questions that are actual questions that you have. I mean, we presume that none of you are experts in this material and that you'll have lots of questions. And, I think Gavin has jumped in a few places to sort of help direct things. But, we can't sort of help clarify what we don't know is, what we're not aware of is confusing for you. So please use those discussion questions as an opportunity to, share with others and with us, where you're getting confused, where you're getting lost. And I think it would be shocking if there weren't many other students, in the same boat. Very few of you have asked questions that are just shockingly novel, in the sense of suggesting that you and you alone have these questions. Similarly, with responding, with offering your comments and your responses to other people's questions, please take the time to be engaged and to think about the material a little bit. It will pay off. All we can do is tell you that, having done this course before many times and courses like it, it does pay off to stay engaged with the material, to ask questions that you actually have, and to take the time to respond to your fellow students. Not only because your grade, will be better, but because you're likely to get the material a little bit more, to pick a little bit more out of it. In terms of in the videos, so far you've now seen all 5 episodes of Dawkins's Growing Up in the Universe. We hope you've appreciated hearing those lectures. I mean, this book, in fact, was sort of a reworking and sort of a bringing together of all the material that you heard in those 5 lectures. Once again, I don't know how else to say it, but that you will do better in the course for having watched and thought about those lectures. It's not an exact replication of the book. You will find that Dawkins uses slightly different examples. He presents the material in a slightly different context. And that really is our goal, is to give you multiple avenues to get at this material. So please, if you haven't watched all 5 of those videos, please do. It will be worth your time. I'm sure you guys are aware that if you're so inclined, you can, I believe that even with these videos, you can select 1.5 speed to have it play just a little bit faster. I think you can do that. Can you do that with these, Gavin?
I'm not sure. I actually didn't check because it's not on YouTube that these videos
It's
are.
not on YouTube. Right. Well, at any rate, some of the subsequent videos that we have asked you guys to watch, you can do that. But look, it's not an interminable amount of time that you're investing in these videos, and they really are. You know, we're not in the business of just chewing up your time. I mean, we've been very selective about what we're asking you to watch, and hope that you'll watch them. And honestly, I can genuinely say that they are useful. They're, for the time you invest in watching these lectures, it will pay off. And I don't know how else to say that. We're not interested in, burdening you with busy work or busy watching. So all of that said, this is a summer course and things move quickly. Clearly, we're now into chapter 5 of Dawkins's book. Where after today will be actually after today. So we've got one more week with Dawkins, and then we will shift over to the goodness paradox, the strange relationship between virtue and violence in human evolution. The whole point of beginning with Dawkins and beginning with some foundational, sort of issues within evolutionary science is to sort of set the stage for a discussion of virtue, goodness, altruism, cooperation, as contrasted with, violence and nastiness. Both sets of concepts of which are part of the human, the human predicament. You will find in Wrangham's book that, he's going to talk about humans, but you will hear lots about many other primates, especially chimpanzees and bonobos. And all through the next book, Wrangham will weave in concepts, ideas, and issues that have been discussed in Dawkins. So it's important to spend the time with Dawkins to sort of set the stage for applying these evolutionary concepts. So again, with Dawkins, it's really just getting the groundwork on what is evolution by natural selection, what is an adaptation, how does evolution by natural selection work, and then we'll apply these ideas specifically to humans and specifically to virtue and violence. All right, is there anything else we want to say, Gavin, before we get rolling?
No, not that I can think of.
All right. So, chapter 5 in Dawkins is titled The 40-Fold Path to Enlightenment. And this is a lengthy chapter, but I think we can, sort of pull out the main issues and main sort of points of this chapter. The point of this chapter from our perspective, that is from my perspective and Gavin's perspective, is not to bury you in details about the structure and functioning of eyes. Eyes are an example of a complex adaptation that must have evolved in gradual steps. And in fact, the eye, either the human eye or a complex eye, let's just take the human eye, was held up by William Paley and others before Darwin as something that was impossible to explain by anything other than God. And in fact, it was held up as an example of sort of a majestic work of God. And to be fair, before Darwin, there was no other explanation for this kind of complicated design. I mean, you now have read a little bit about rods and cones and lenses, and corneas, and eyes are incredibly complex. But it wasn't until Darwin that there was an alternative explanation, a naturalistic explanation for the evolution of eyes. And if you can explain something as complex as the eye from an evolutionary perspective, well, then there's little else left, because it is an extraordinary adaptation. And one of the things that Dawkins is communicating in this chapter is that not only can the eye evolve by gradualistic, by gradual steps, by tiny increments, tiny changes, over evolutionary time. Not only can it evolve, but in fact, there's wonderful evidence that it has evolved, that an eye has evolved at least 40 times independently across a huge range of species. And that's the reference to the 40-fold path to enlightenment. Eyes have evolved independently, that is, along different independent paths over evolutionary time at least 40 times. There's some suggestions that it may have been closer to 60 or even 70 times. So not only is it not impossible for the eye to have evolved, but it's likely that an eye, different structures, different forms of eyes have evolved dozens of times. So it's not something extraordinarily unlikely to have occurred, given what we know. Struggling with the camera, Gavin?
Yeah, I'm trying to block out some of the light.
It's okay. I'm from what I'm viewing, it looks okay. Mine's
okay. I was getting like rays coming in from my top right corner. That's actually a lot better.
I thought that was just your natural goodness. Okay. Okay, so Gavin, does that sort of summarize sort of the broadest picture of this chapter?
Yeah, no, it definitely does. And I tried to make a lot of the same sorts of points when I was talking about the wing.
Excellent.
Or wings last week.
Yes.
And I think, I don't know, I'm not sure where specifically you wanted to sort of take the time to explain the details, but I think generally my impression of this chapter was that Dawkins' reasoning for going through the different details of how different parts of the eyes could have and likely did develop gradually, and how each step of that gradual development of the many layers of photoreceptors in eyes, or in like bundles of neurons at the back of eyes, and the gradual progression of a transparent type of lens on top of an eye in order to enhance images in such a way that it makes it easier to see without narrowing the opening through which light can pass, with his example of the dolphin. All of the sort of excruciating detail Dawkins goes into is just in service of explaining exactly what you said, which is that even something as complicated as the eye can and did evolve in very gradual steps over, a long period of time, but as he explains in the chapter, evolutionarily speaking, not really that much time.
Right. Yeah, and furthermore, not only can it evolve, but all the evidence suggests that an eye did evolve, that eyes did evolve, do evolve, not just once, but dozens of times. And again, when some of that computer programming work, where they sort of rig up, they run a program to see how long would it take to evolve something like this. You get something like, isn't it like 200,000 generations or something?
Yeah, something like that.
Yeah, 500,000 years or something like that, which, of course, from the perspective of a human life, which is 70 or 80 years, seems like an extraordinary amount of time, but it's a blink, it's an eye blink, in evolutionary time. 500 million years is not, if that is the time period. Anyways, millions of years are relatively trivial in terms of the time period available for life to have evolved, or for eyes to have evolved. And so there certainly is plenty of time available. All the evidence suggests that eyes have evolved dozens of times. It's not an impossible task by any means. And that's part of what Dawkins is communicating here, is that we're not dealing with something that is so extraordinarily rare that we're fumbling for any kind of sort of application of evolutionary thinking. It is, you know, there's just no insurmountable sort of walls here. Well, there's no insurmountable sort of leap that one has to make up Mount Improbable, so long as there are pathways, okay, by which the eye can evolve gradualistically, and all the evidence suggests that those paths were there and are there. And I want to call attention to one thing. So on the bottom page 140, he's sort of setting things up, and I think there's a couple of points here. He says, this is the last paragraph on page 140. He says, as I survey the diversity of animal eyes, I'll often mention whereabouts on the slopes of Mount Improbable each type is to be found. Remember, though, that these are all eyes of modern animals, not of true ancestors. It is convenient to think that they might give us some clues about the kinds of eyes that ancestors had. They do at least show that eyes that we think of as lying halfway up Mount Improbable would actually have worked. This really matters, for, as I have already remarked, no animal ever made a living by being an intermediate stage, by being a stage on some evolutionary pathway. So one of the things that Dawkins does is he points out, and Darwin did something very similar in On the Origin of Species. Dawkins presents examples of what we might think of, just for the moment, as sort of 1/10 of an eye, or 2/10 of an eye, 3/10 of an eye, 4/10 of an eye, and he gives you examples of actual organisms that have sort of would-be eyes or partial eyes on the way to what we think of as the most complicated eye, the human eye, or an eagle eye. And so the fact is, there already are animals out there with, let me just speak colloquially, there already are animals that do wonderfully with, quote, half an eye, unquote. And so one needn't sort of demand that the eye evolves, the human eye evolves fully formed and poofs into existence with all of its complicated contrivances, because there's clear evidence that eyes that don't have all those complicated contrivances can work perfectly well under this particular circumstances for a particular species. So one of the gravest pushbacks on Darwin's account of the eye, and one of the reasons why William Paley and many of the natural theologists before Darwin, argued that the eye was proof of God, was the argument that the eye would have to have come into existence totally, fully formed, as complex as we see it right now in the human or in an eagle, and that partial eyes couldn't work. It wouldn't be possible. It'd have to all happen at once, and that would require a miracle, and therefore God. But that's simply not the case. All of the complicated architecture of the human eye exists, sort of metaphorically speaking, in parts, in many species, hundreds and hundreds of species today, throughout the world, bits and pieces of what we see as the complex human eye. Now, that doesn't prove that evolution by natural selection occurred, but it does document that so-called half an eye could work perfectly well, or a quarter of an eye, or a tenth of an eye, and so on. Have I been clear there, Gavin?
Yeah, no, I absolutely think you have. And I also think it's sort of worth looking at it from the opposite end, so to speak. So instead of, using the ability of an eye to evolve gradually and for each step to be beneficial to the animal who owns it, I also think it's worth saying, if you first start with the assumption that evolution by natural selection is true, and then look at the eye, you sort of have to conclude that for it to evolve any other way is impossible, or for it to have occurred any other way is impossible, because for natural selection to work as it does, each individual gradual step has to be beneficial. So it couldn't have gotten the eye in humans or eagles couldn't have gotten to where it is without each successive step backwards, or each slightly less uh, improved or ideal version backwards in history, must also have been beneficial.
Right. Absolutely.
So,
And I like the section. On page 150. He really showcases. He sort of zeroes in on gradualism, on gradualistic change over time. That is no huge leaps, no so-called hopeful monsters. All of this is designed to push back against the idea that that complicated architecture, complicated adaptations poof into existence, fully formed. Okay, that's not the way evolution by natural selection works. It works in all but imperceptible changes over huge, amounts of time. All but imperceptible, because at the time you wouldn't see any difference to what is happening. You only notice the differences that are happening looking back. And for example, if you have a workable fossil record. But on page 150, he says, this is the last paragraph from page 150. He's sort of gone through the pinhole effect, but he says the pinhole effect is just an extreme version of the cup effect that we've already met as an aid to telling the direction of light. It belongs only a bit farther up the same slope of Mount Improbable, and there are no sharp precipices between. Then he says here, there is no difficulty in a pinhole eyes evolving from a cup eye, okay? And no difficulty in a cup eyes evolving from a flat sheet of photocells. The slope up the mountain from flat carpet to pinhole is gradual and easily climbable all the way. No magic required here, no miracles. Climbing it represents a progressive knocking out of conflicting images until at the peak, only one is left. Okay, and then he further points out pinhole eyes in varying degrees are indeed scattered around the animal kingdom. So the other main message in this chapter is that no miracles are required. No miracles are required for complex architecture to evolve, to appear. Okay, that's the only you aren't stuck with one option, which is that if you have something complicated, well, then it must be a miracle, and therefore God did it. The whole point of this chapter, okay, and many previous chapters in some ways, is pushing back against the idea that there's only one way up Mount Improbable, and that is a miraculous leap up thousands of feet to the top. Because as Dawkins, suggests, if you simply look around the other side, okay, there's a gradual slope that take one step at a time, and you can get to the same place with no miracles. Okay. All right. A lot of this, I think, as Gavin mentioned, and as we've mentioned, is providing some background details, some context for the examples that he's giving, the sort of meat to the bone, I suppose, of eyes and the features of eyes. I just happened to stumble upon page 158, where he says, again, just sort of hammering home this issue. He says it is in the middle of page 158. It is not difficult then, he says, for rudimentary lens-like objects to come into existence spontaneously. Okay? Yes, some traits, some details come into existence spontaneously, but these are incredibly simple details. Okay? He says any old lump of halfway transparent jelly need only assume a curved shape. There are all sorts of reasons why it might, and it will immediately confer at least a slight improvement over a simple cup or pinhole. And here's really the kicker. He says slight improvement is all that is required to inch up the lower slopes of Mount Improbable. Okay? Improvement of such a degree that you wouldn't even notice it at the time, okay, if you or any organism were around noticing such things.
right, and I think that that example sort of mirrors his when Dawkins was talking about the halteres or the wing nubs in the last chapter.
That's right.
So just talking about how very, very small differences, and it's necessary for him to make this point because he has spent a lot of the book up to this point talking about how mutations are, random mutations like the ones that wings would have started as, or that lenses and eyes would have started as, would have been extremely small because that's how spontaneous random mutations occur at first, and then gradually become, the lenses that we have today. But of course, they need to start as very small lumps of, whatever clear vitreous material or whatever he says. But it's not, for that to occur is not that huge of a feat. And he talks about how the shape sort of would have became lens-like more or less naturally, and how there wouldn't have, like you said, there wouldn't have needed to have been that much in order to incur some very small benefit, and that's all that's needed in order to be passed down to offspring.
That's right. Yeah, that's right. Yeah, I think that's true. One could argue, well, why do we need a chapter on wings, given that we have a chapter on eyes? Where was that chapter on wings? Was that
the previous chapter?
Yeah. But again, there's something to be said for hearing about these concepts and ideas, with different examples, under different conditions, with different species. And that, that of course is precisely what he's attempting to do here. There are, many people who, just to give you an example, there are people who can't quite, don't quite appreciate the arguments when applied to wings or flight. But once he does so with regard to vision and the eye, something clicks for them, or vice versa. They have trouble hearing about this with regard to an eye, but having heard about, the evolution of flight, now, they have a sense. And that's really what he's doing here. There's no, at least for our purposes, we're not asking you to bury yourself in, all of the details of wings or eyes, but instead to see the bigger picture. Speaking of the time periods involved, I think this is a nice section that really kind of, summarizes what we were talking about in terms of the length of time required for the evolution of something like an eye. And it begins on 165 and it continues on 166. I'm going to pick it up sort of in the middle of page 166. He says, let me start closer to the top of that page. He says, a skeptic about the power of evolution, such as Emma Darwin, Charles Darwin's wife, she was a skeptic, and specifically about the power of evolution to explain something like an eye. So such a skeptic, according to Dawkins, is naturally drawn to the view that an organ as notoriously complicated and many-parted as an eye, if it can evolve at all, will take an immense time to evolve. Well, these researchers, Nielsen and Pelger, their final estimate using this computer program, and much work has been done since the book was published, their final estimate was actually astoundingly short, says Dawkins. At the end of the calculation, it turned out that it would take only about 364,000 generations to evolve a good fisheye with a lens. It would have been even shorter if they had made more optimistic, and this probably means more realistic, assumptions. So then Dawkins says, well, how long is 364,000 generations in years? That depends, of course, on the generation time. The animals we're talking about would be small marine animals like worms, mollusks, and small fish. For them, a generation typically takes a year or less. So Nielsen and Pelger's conclusion is that the evolution of the lens eye could have been accomplished in less than 500,000 years. 500,000 years. And that is a very, very short time indeed by geological standards. It is so short that in the strata of the ancient eras we are talking about, it would be indistinguishable from instantaneous. Okay? The plaint or the complaint that there hasn't been enough time for the eye to evolve turns out to not just be wrong, but dramatically, decisively, ignominiously wrong. Okay? There's plenty of time for the evolution of something as complicated as an eye.
Right. Yeah, it's almost like shocking how when he puts it like that, how short it would have been. And I do think, or I guess I worry a little bit, that may sound a little misleading to some students. I don't want it to sound like Dawkins is saying that, large mutations happen instantaneously. Just that even in the sort of process of natural selection, working on gradual step-by-step changes, those small baby steps up the back of Mount Improbable, large changes can happen over what he describes here as a geologically short amount of time, relative to the time scale of life on Earth. So I hope that makes sense.
It does. So he's using, right, it's instantaneous, metaphorically speaking. Given that we've got billions of years to work with, 500,000 years is a drop in the bucket of time available, right? You can do both things. You can recognize that, wow, that's a long time. 500,000 years, that sure is a long time. Yes, from the time span of, the human life, which is 80 years, 500,000 years is a long time. But you have to put that into the context of what time is available. I mean, there are billions of years available. And in that sense, 500,000 years or 364,000 years is not a notably long period of time. All of which is to say, there's absolutely plenty of time available to inch one's way up Mount Improbable from, a light-sensitive cell to, the equivalent of a complex human eye. Okay? Again, no miracles are required. Moving forward, there's a couple of other points I want to make, from my perspective, Gavin, on this chapter. On page 190, I want to highlight what Dawkins highlights. He says, this is the last chapter on page 190. He says, a central message of this chapter is that eyes evolve easily and fast at the drop of a hat. Okay, he says, I began by quoting the conclusion of one authority that eyes have evolved independently at least 40 times in different parts of the animal kingdom. On the face of it, this message might seem challenged by an intriguing set of experimental results recently reported by a group of workers in Switzerland associated with Professor Walter Gehring. He goes through these experiments, but more to the point, one of the key issues or points that he's focusing on, that he wants to communicate in this chapter, is that eyes evolve, relatively speaking, easily and fast at the drop of a hat. Again, in the context of geological time. And then moving forward just a little bit further, let's see. Okay, so I don't want to belabor the details of this experiment, of this series of experiments by Gehring and his colleagues. But on page 194, Dawkins sort of brings it back to what is the point of telling you about these experiments. He says, this is the middle of page 194. What does this spectacular series of experiments mean for our conclusion in this chapter? Were we wrong to think that eyes have developed 40 times independently? I don't think so. He says at least the spirit of the statement that eyes evolve easily and at the drop of a hat remains unscathed. These experiments probably do mean that the common ancestor of Drosophila, mice, humans, sea squirts, and so on, had eyes. The remote common ancestor had vision of some kind, and its eyes, whatever form they may have taken, probably developed under the influence of a sequence of DNA similar to modern EY, that particular gene. But the actual form of the different kinds of eye, the details of retinas and lenses or mirrors, the choice of compound versus simple, and if compound, the choice of apposition or various kinds of superposition, all these evolve independently and rapidly. We know this by looking at the sporadic, almost capricious distribution of these various devices and systems dotted around the animal kingdom. Okay, he says, continue on page 195, in brief, animals often have an eye that resembles their remoter cousins more than it resembles their closer cousins. The conclusion remains unshaken by the demonstration that the common ancestor of all these animals probably had eyes of some kind, and that the embryonic development of all eyes seems to have enough in common to be inducible by the same DNA sequence. Okay, finally, on page 176, towards the very end of the chapter, he says, Dawkins notes, nothing is as difficult to evolve as we humans imagine it to be. Okay? Darwin gave too much when he bent over backwards to concede the difficulty of evolving an eye. And his wife, Emma, took too much when she underlined her skepticism in the margin. Darwin knew what he was doing. Creationists love the quotation that I gave at the beginning of this chapter, but they never complete it. After making his rhetorical concession about how difficult it is for the eye to evolve, Darwin went on. And here's Dawkins quoting Darwin. Darwin says, and again, this is in 1859, when his book was published, and he's just finished talking about, it seems all but impossible for an eye to have evolved, right? And then he goes on to say, Darwin does, when it was first said that the sun stood still and the world turned round, the common sense of mankind declared the doctrine false. But the old saying of vox populi, vox Dei, as every philosopher knows, cannot be trusted in science. Reason tells me, says Darwin, that if numerous gradations from an imperfect and simple eye to one perfect and complex, each grade being useful to its possessor, can be shown to exist as is certainly the case, the eye ever slightly varies, and the variations be inherited, as is likewise certainly the case, and if such variations should ever be useful to any animal under changing conditions of life, then the difficulty of believing that a perfect and complex eye could be formed by natural selection, though insuperable by our imagination, cannot be considered real. In other words, he's saying it may be difficult to conceive, but by the brute force of logic, it's not impossible. Okay, anything else we want to add on the 40-fold path to enlightenment?
No, I think we hit on the broad, like the main message of the chapter.
Okay, I do too. I think, there's lots of details that, aren't necessary. They might be extremely helpful, but they aren't necessary. They're not necessary for this class anyways,
right.
Given that this isn't a class on the evolution of the eye. Okay, so let's shift to chapter 6, the Museum of All Shells. Part of what Dawkins is doing in this chapter is attempting to give the reader an appreciation for what is possible, okay, and what actually occurs. And what actually occurs is the result, in large part, of natural selection, of selection pressures, moving an organism or moving a trait along one path rather than another. And we'll sort of, we'll unpack that as we move through here. And I want to do that in a way similar to what we did for the previous chapter and what you did, Gavin, for the chapter on flight and wings. Once again, I don't want to get buried in details, but I do want to bring to the front sort of the main issues and the main sort of points of this. So he begins by saying, natural selection is the pressure that drives evolution up the slopes of Mount Improbable. Okay? Pressure really is a rather good metaphor, he says. We speak of selection pressure, and you can almost feel it pushing a species to evolve, shoving it up the gradients of the mountain. Predators, we say, provided the selection pressure that drove antelopes to evolve their fast-running legs. Even as we speak, though, we remember that what this really means. Genes for short legs are more likely to end up in predators' bellies, and therefore the world becomes less full of them. Pressure from choosy females drove the evolution of male pheasants' sumptuous feathers. What this means is that a gene for a beautiful feather is especially likely to find itself riding a sperm into a female's body. But we think of it as a pressure driving males toward greater beauty. No doubt, predators provided a selection pressure in the opposite direction, towards duller plumage, since bright males would presumably attract predators as well as female eyes. Without the pressure from predators, the cocks, that is the male birds, would be even brighter and more extravagant under pressure from females. Selection pressures then can push in opposite directions, or in the same direction, or even, he says, mathematicians can find ways of visualizing this at any other angle relative to one another. Well, I've now read most of this, so let me finish this paragraph. Selection pressures, moreover, can be strong or weak, and the ordinary language meanings of these words fit well. The particular path up Mount Improbable that a lineage takes will be influenced by lots of different selection pressures, pushing and tugging in different directions and with different strengths, sometimes cooperating with each other, sometimes opposing. Then he says that pressure isn't the end of the story. The path chosen up Mount Improbable will depend too on the shapes of the slopes. And then at the end of that paragraph, or in the middle of that paragraph, he says selection pressures, however strong, can't do anything without genetic variation. Okay? And he asks us to visualize a museum of all possible animals. Okay, this is beginning on page 200. Thinking of a way to try to jump into this. Let's see. He says, I'm trying to avoid reading too much, but some of this is said so eloquently, it's hard to replicate. So he says, imagine, this is in the middle of page 200, imagine a museum with galleries stretching towards the horizon in every direction. Okay, and as far as the eye can see, upwards and downwards as well. Preserved in the museum is every kind of animal form that has ever existed and every kind that could be imagined. Many of these kinds, of course, will not have ever existed. Each animal is housed next door to those that it most resembles. Each dimension in the museum, that is, each direction along which a gallery extends, corresponds to one dimension in which the animals vary. For example, as you walk north along a particular gallery, you notice a progressive lengthening of the horns of the specimens in the cabinets. Turn round and walk south and the horns shorten. Turn and walk east and the horns stay the same, but something else changes. Say the teeth get sharper. Walk west and the teeth grow blunter. Since horn length and tooth sharpness are only two out of thousands of ways in which animals can vary, the galleries must crisscross one another in many dimensional space, not just the ordinary three-dimensional space that we, with our limited minds, are capable of visualizing. This is what I meant when I said that we had to learn to think like a mathematician. So he's setting us up to think in terms of how can animals vary? Okay, this is the museum of all possible animals, only a small portion of which actually will have existed and do exist. Okay? The pathway through that museum of all possible animals, one pathway or one set of pathways are those animals that do exist or did exist. And it will be but a small portion of all possible animals. And those that did exist are the result of selection pressures. Okay? Some animals, with horns and, horns that are 30 feet long could exist, but never did exist because the relevant selection pressures weren't there. Or they may have been there, but there were pressures pushing back against the evolution of those extraordinary sorts of traits. I mean, you can imagine that if in males, lengthier horns are more attractive to females, that would provide the selection pressure for the evolution of lengthier horns in males. But of course, evolving lengthy horns has its costs. It becomes difficult to navigate, difficult to walk, never mind run, if you're trying to drag along, 30-foot horns. So that would be selection pressure against the evolution of longer horns. So what you actually see, in terms of what exists or what did exist, is only a small portion of what could have existed. Only a small portion of all possible animals. And I think, just before I forget, I like this diagram, just for the purposes of this particular example, on page 210. This is what Dawkins refers to as Ropp's cube. The bottom line is, and this is actually applied to shell, I believe, flare, which is a flare, spire, and different qualities, verm of shells. The cube itself represents all possible variations. The shaded area shows the actual existing shells with those different qualities. And you can see it's just a very small portion of the cube that is actually shaded in. That is the result of, sort of the cascade of consequences of multiple selection pressures. So only a small portion of that cube is filled in with existing or real organisms. Those organisms are the results of selection pressures, that were expressible in terms of actual living organisms.
Right. And I think, correct me if I'm wrong, but I think he sets up this chapter by posing like the hypothetical question, do we not see most of this cube filled out because many of the mutations would not have, or many of those shell types would not have randomly mutated, or because they wouldn't have incurred an adaptive benefit for the animal that owned it, right? Is that, I think that's...
Yes.
Okay.
So those are two not mutually incompatible ways to, or of understanding what exists. One possibility, why don't you see animals with 30-foot, horns? Well, one potential explanation is, well, there never were selection pressures, or the natural selection pressures were such that 30-foot horns could not have been produced in the context of an animal that could function and could live and could survive and reproduce. So it's a selectionist sort of explanation. An alternative explanation, or at least a potentially alternative explanation, it's often presented as an alternative explanation, is that, well, the genes that build those giant, those really long horns just never existed. There never was the relevant genetic variation. And, Dawkins isn't ruling out the possibility that an absence of the relevant genetic variation might help to account for why you don't see something. What he's proposing is that we can often go farther by taking first on board the idea that the selection pressures either weren't there, or the selection pressures were, sort of combated by alternative or additional selection pressures. But again, I think one need not choose sides. Both explanations, genetic variation and selection pressures, are relevant and can help get us to, the full explanation.
Okay.
Yeah. Let's see. So a lot of this chapter is designed to sort of communicate to the reader, in part, what's required for evolution by natural selection to occur. What is the role, or what are the roles of selection pressures, of heritable variation, and how do we account for the distribution of life in terms of what traits are possible and what traits actually exist. And one of the ways he sort of summarizes, I think this is actually a difficult chapter, not because the material is necessarily difficult, although it's probably material that many of the students aren't familiar with. But it's a slippery idea. And what he says here, so bringing this home, on page 222, towards the end of the chapter, he says, okay, this is actually towards the beginning of page 222. Difficult as it is to visualize the myriad-dimensioned museum of all possible animals, it is easy to keep in our heads the simple idea that animals are housed near those that they most closely resemble. Okay, I hope that students can appreciate that fact. All possible cheetah-like animals will be housed in this museum of all possible animals very, very close together, right? Because each one is literally a very simple variation on the one next to it, right? And so he says, it's easy to keep in our heads the simple idea that animals are housed near those that they most closely resemble, and that it is possible to move in any direction, not just straight along corridors. An evolutionary history is a snaking trajectory through some part of the museum. Since evolution is going on independently in all parts of the richly diverse animal and plant kingdoms, we can think of thousands of trajectories tunneling in different directions through different regions of the multidimensional museum. And then he says, parenthetically, notice how far we have come from the very different metaphor of Mount Improbable. Now, the controversy, he says, with which we began can be re-expressed as follows. He says, some biologists feel that as you walk along the corridors of the museum, what you will find is smooth gradations in all directions. Large portions of the museum are never, as a matter of fact, visited by living flesh and bone. But according to this view, they would be visited if only natural selection, quote, wanted to nose its way into those portions. A different set of biologists, with whom I am less in sympathy, but who may be right, feel that large portions of the museum are forever barred to natural selection, that natural selection might batter eagerly on the doors of a particular corridor, but never be admitted because the necessary mutations simply cannot arise. So he's summarizing those two perspectives there. Other portions of the museum, according to an imaginative variant of this view, far from being barred to natural selection, act like magnets or sinks, sucking animals toward them, almost regardless of natural selection's best efforts. The Museum of Possible Animal Forms is not an evenly laid out mansion of long galleries and stately corridors with smoothly changing qualities, but a set of well-separated magnets, each one bristling with iron fillings. Okay, he continues on and he says, I have an open mind about this controversy, although I lean in one direction. On one point, though, I insist. This is that, and this really is a crucial point that he's leaving you with in this chapter. He says, this is on page 223, this is that wherever in nature there is a sufficiently powerful illusion of good design for some purpose, natural selection is the only known mechanism that can account for it. Okay? Yeah, just because this is such an important statement, let me just say it again. And this is purely Darwinian. This could have been a sentence that Darwin himself wrote. And it is a statement about evolutionary science that is fundamental to understanding, the evolution and, the complex nature of any adaptation. So he says, on one point, I insist. He says, this is that wherever in nature there is a sufficiently powerful illusion of good design, like the eye, for example, or the structure of the ear, okay? And it appears to be so beautifully designed for hearing, okay? Whenever that occurs, okay, apparent good design for some purpose, natural selection is the only known mechanism that can account for it. No amount of genetic just happenstance, accidental variation, attractors sort of sucking animals towards a particular form, none of that can explain complex design, okay, as cleanly and as efficiently, okay, as natural selection. Okay, anywhere you see apparent design, what appears to be design, in other words, something that a god must have created, it's just that. that natural selection must explain, does explain. We simply have no scientific alternative. And he goes on to say, magnets or attractors in animal space cannot, unaided by selection, achieve good functional design. Okay, there's a lot of work. This is part of what Dawkins is doing here. There's a lot of work on, biologists or others in cognitive science or philosophy saying, yeah, you don't really need natural selection. I think they're misguided, but I think what they really mean to say is natural selection alone can't explain, the distribution and the form of all of life. That's true, but natural selection is required to explain complex apparent design. It's fine and well if you want to add meat to the bone of that explanation and say, and talk about attractors or, accidental genetic variation. But still, if you want to explain complex design, there's nothing for it but to revert to natural selection. Natural selection operating over evolutionary time is the only known scientific cause of apparent design.
Right. And so when you say that, they may be right in that natural selection may not be able to account for all of the variation
Right.
in life, but for complex design, you're talking about, when natural selection works on sort of a certain trait or builds a sort of complex, multifaceted organ like the eye or wings or something like that, such that natural selection would had to have favored a better version or a better model of that organ or of that structure generation after generation, such that it created the complex structure that is whatever is in question.
Yeah, that's right. So natural selection is required to explain the big picture fact of complex apparent design. Now, there are plenty of details about that complex design could have turned out differently. Okay, but these are the relatively trivial details. Okay, whether the horns on males, at the ends curved out or curved in, for example. There's a place for understanding some of the features of adaptations on the basis of the genes that were available on which to select. Okay, but still, you can't get anywhere in terms of complex design without recourse to evolution by natural selection. It's selection pressures operating over evolutionary time that account for apparent design for purpose. Some of the more trivial, I would say, some of the trivial details surely can be attributed to what genetic variation was available. Okay? But it is misguided to think that it's the genetic variation that's available that gives you the apparent design. Okay? It's selection operating over evolutionary time that gives you complex design. Some of the details, an NE versus an Audi, moving right versus left, or turning right versus left, those details may well be accounted for by, what genetic variation was available just by happenstance.
Okay, that's a good way to put it, and I think it's a good way to help sort of frame this chapter, because I like you said, it's a little slippery.
It is.
I definitely felt myself struggling in places to grasp like the bigger picture of this chapter.
Yes, and I've read this chapter, probably 30 times, and I think it is. This chapter, maybe more than any other chapter. It's the most important thing we're doing here is trying to get at the central message. And, it's easy to lose track of the central message if you're not steeped in this literature. So I think that's our role, is to help students find the forest for the trees. Yeah, and the forest for the trees. So, yeah, I mean, I think to Dawkins's credit, what he's doing is he's recognizing that there's an apparent, and it's really not a pushback on natural selection for complex adaptation. Sometimes it's presented as some sort of alternative to natural selection. You hear things like genetic drift, or genetic happenstance, or attractors. And oftentimes when people are presenting these as explanations for life, they think they're offering an explanation that is an alternative to natural selection. Okay, but it's not. It's not an alternative to natural selection. It does not. These explanations that rely on genetic variation or genetic drift or attractors, or this sort of these sorts of ideas, ultimately go nowhere in terms of building complex design. You still need, natural selection as the main mover up Mount Improbable. Now, whether you, at a fork in the road up Mount Improbable, whether you go right or left may well depend on the genetic variation that's available. But you still need natural selection as an explanation for how you get up that path.
Right.
Yeah, okay. All right, let's move on to the last chapter for today, and that is kaleidoscopic embryos. I think this also could be a very difficult chapter, but it does not need to be, and I'll tell you what I mean. Bottom line, what Dawkins is presenting is the argument that embryological development, the details of embryological development may make some animals or some classes of animals or some entire, families of animals more likely to evolve. Okay, by virtue of the nature of embryological development, some animals may be more susceptible to evolution, than others. Once again, this is not an alternative to natural selection. It's adding meat to the bone. You still have to have a mechanism by which some traits are favored over others. But that's not to say that you can't have embryological details that make evolution more or less likely. Okay, so let's look at this chapter for just a minute here. Okay, so he says, I think I'm going to have to start at the beginning of this chapter. So he says, kaleidoscopic embryos, this is chapter 7. He says, bodies are built by the processes of growth, mostly in the embryo. So a mutation, if it is to change the shape of a body, will normally do it by adjusting the processes of embryonic growth. A mutation might, for instance, speed up the growth of a particular piece of tissue in the embryonic head, resulting eventually in a lantern-jawed adult. Changes that occur early in fetal development can lead to dramatic knock-on effects later on. 2 heads, perhaps, or an extra pair of wings. Such drastic mutations, for reasons that we saw in chapter 3, are unlikely to be favored by natural selection, because these drastic changes typically will result in death. Okay? In this chapter, I'm making a different point, he says. This is that the kind of mutations that are available for natural selection to work on will depend upon the kind of embryology that the species possesses. Mammal embryology works in a very different way from insect embryology. There may be analogous though smaller differences in the types of embryology adopted by different orders of mammals. And the point I want to come on to is that some types of embryology may, in some sense, be, quote, better at evolving than others. I don't mean more likely to mutate, which is another matter altogether. I mean that the kinds of variations thrown up by some types of embryology may be more evolutionarily promising. than the kinds of variations thrown up by other types of embryology. Moreover, a form of higher level selection, what I have previously dubbed the evolution of evolvability, may lead to the world becoming peopled by types of creatures whose embryologies made them good at evolving. And he says here, coming from a dyed-in-the-wool Darwinist like me, this might sound like the rankest heresy. Natural selection is not supposed in nice neo-Darwinian circles to choose among large groupings. And didn't we agree in chapter 3 that natural selection favors a zero mutation rate, which fortunately for the future of life it never reaches? How can we now claim that a particular kind of embryology might be, quote, good at mutating? Well, perhaps in the following sense, and this really sort of summarizes what he's about to get into. Certain kinds of embryology may be prone to vary in certain ways. Other kinds of embryology tend to vary in other ways. And notice there's no magic here. And some of these ways may be in some sense more evolutionarily fruitful than others, perhaps more likely to throw up a great radiation of new forms, as the mammals did after the dinosaurs went extinct. It is this that I meant, okay, when I made that rather odd suggestion about some embryologies being, quote, better at evolving than others. What he's getting at here is the notion that embryological development, the nature of embryological development, can make a class of animals or organisms, a huge group of organisms, more likely, okay, to evolve in more and different directions. Okay, none of which speaks against the power of natural selection as the explanation for apparent design.
Right. And so, I mean, the main point of this, or a lot of what he spends time explaining in this chapter is about symmetry. So, is he saying that animals or types of animals with embryology in which they develop body structures symmetrically on usually their limbs, or when he talks about insects later on, their different body segments, is he saying that animals with those kinds of embryologies, where structures get sort of copied or mirrored on the other side, are better in that way?
Yes, or more likely to throw up, as he says, to throw up the relevant variation that may be more likely to be selected to be favored by natural selection.
Okay.
Yeah, and so, yeah, well, if you think about, right, so you have symmetrical forms and you have segmented forms. These types of embryologies are extraordinarily open to many new and different paths in, the Museum of All Animals. In a way that the asymmetrical animals, embryological, the animals that develop embryologically in, with peculiar asymmetries, the same number of paths simply aren't open to them. There's a lot of metaphorical walls when you're operating, when your embryology is asymmetrical rather than symmetrical. Let me think of another way to say this. Well, let me see if this helps. The very end of this chapter, okay, he says, and let me highlight this last chapter. I think it's going to be very useful for summarizing a lot of this detail. Okay, he says, so on page 255, the central message of this chapter, okay, is that kaleidoscopic embryologies, segmental embryologies, symmetrical embryologies, things that can sort of blossom, towards the right and towards the left, or forward as well as backwards, where there's lots of ways to very, very simply add to what's already there. Okay. 5. Sorry, I just lost my spot. He says, the central message of this chapter is that kaleidoscopic embryologies, whether working through segments and clusters of segments, arranged in a line from front to rear, as in an insect, or through mirrors of symmetry, as in a jellyfish, are paradoxically both restrictions and enhancements. Okay, they restrict evolution in that variation available for selection to work upon. Okay, they enhance evolution in that, to put it in a language that personifies selection forgivably, they save natural selection from wasting its time exploring vast regions of search space which are never going to be any good anyway. The world is populated by major groups of animals, arthropods, mollusks, echinoderms, vertebrates, each one of which has a form of kaleidoscopically restricted embryology which has proved evolutionarily fruitful. Kaleidoscopic embryologies have what it takes to inherit the Earth. Whenever a major shift in kaleidoscopic mode or mirror has spawned a successful evolutionary radiation, that new mirror or mode will be inherited by all the lineages in that radiation. This is not ordinary Darwinian selection, but it is a kind of high-level analogy of Darwinian selection. It is not too fanciful to suggest, as its consequence, that there has been an evolution of improved evolvability. So, I mean, once again, this is a slippery concept, but what he's arguing is that, yes, in some sense, the embryology of a group of animals, the way an embryo develops, embryogenesis, the development of the embryo, okay, from a fertilized egg, for example, to a fetus, okay, sets the stage for the path of evolutionary change, but it does that by both enhancing and restricting what's possible. And I think it's, part of what Dawkins is doing is recognizing that there are apparent controversies and alternatives to explaining evolutionary change over time in large groups of species. Some have argued, well, it's all about, what is possible, an embryology that makes evolutionary, change more likely. And it does that by, by a particular type of embryogenesis that enhances or allows evolution to occur. But an equally correct group of biologists would argue, oh, no, it's not about enhancing what could occur, it's about restricting what might occur. I mean, part of what Dawkins is communicating is it's not clear that these two groups of people are really saying anything that's fundamentally different. Any path for potential evolutionary change, yes, it both enhances the likelihood of that change occurring, but by the same token, restricts it from occurring otherwise, in some other way.
Right.
But it really is the case that part of what Dawkins is sort of showcasing is the notion that, well, in part, none of this is relevant to the fact that complex adaptation is explicable or must be explained with reference to natural selection. Okay? Yes, we can talk about the evolution of evolvability. We can talk about, some embryologies being more or less open to or amenable to evolutionary change. But that's all sort of surface level, sort of disagreements of emphasis, because everyone agrees that natural selection is the only known scientific cause for adaptation, for complex apparent design. And so, in many ways, I'm not suggesting that this isn't an important area of biology or of evolutionary science, embryology. It's huge. It's a huge area, and it's an area that Darwin himself, laid some emphasis on. But Dawkins is encouraging the reader not to lose sight of the forest for the trees. Um, yes, it's worth being familiar with some of these arguments and some of these different emphases on the importance of embryology and whether it opens certain pathways or closes other pathways. None of which changes the fact that in order to get from the base of Mount Improbable to the top, you can't leap in one fell swoop. You've got to go around the backside and take it step by step. Now, the pathway up Mount Improbable, embryologically speaking, may take you in one direction or a different direction. And there may be some organisms that flourish up the backside of Mount Improbable because of the nature of their embryology, because it opens up some pathways, more pathways than a different sort of embryology. But that's all built on top of, the emphasis and the requirement that, natural selection operates gradualistically, okay, step by step up Mount Improbable, never great leaps. Does that help give some context to this?
It does a lot, actually. For a couple reasons. One main thing I wanted to touch on that I think was helpful in both talking about this chapter and the last chapter on shells is that I sort of worry that for students, they might get hung up in places where Dawkins sort of sets up these hypothetical questions, such as in the last chapter when he talks about, whether animals or organisms evolve in a certain direction, because of the mutations available, just strictly speaking, the genetic variation available, or what natural selection favors, and then does a similar sort of thing in the types of body plans or the type of embryologies that are better at evolving, and doesn't give a definitive answer because, the answer in both cases is sort of it depends.
Sure.
And I think you explained that pretty well just now. And I say that all just to sort of bring up the point that I don't want any of the students reading the book and watching this to get hung up in places where he does set up those questions. Then it sort of seems like he doesn't give a definitive answer, because he is sort of, that's not really his goal. He's sort of exploring different options and using examples from different animals to explain the costs and benefits and the reasons why both sides of those issues have merit, if that makes sense.
Yes, absolutely. Look, evolutionary science and embryology and, complex design, I mean, these are, in some sense, very messy topics. And, there are lots of interesting disagreements. There are lots of, potential, alternative emphases. But we're still left with, the importance of natural selection, as the cause of complex adaptation. I mean, what Dawkins is doing is, giving the reader, sort of a reasonable and fair picture of, the range of, sort of perspectives within animal behavior and evolutionary science. And part of what he's doing as a writer, and I think as a scholar, is moving people, helping them appreciate these different perspectives while also helping them see the forest for the trees, or at least helping to guide them towards what we do know in the context of what we don't. I mean, biology, and again, and evolutionary science is and can be very messy in a way that physics is not. And partly that's the nature of living organisms. But I think we've done our part by trying to showcase what is his point in these chapters. Okay? I mean, if nothing else, I think we've said several times, and I think it really is important to don't get bogged down in the details. Okay, please, work to stay focused on the big picture issues. And those big picture issues are typically showcased by Dawkins in the opening paragraph and in the closing paragraph, okay, of these chapters. But again, that's partly why, especially for these last three chapters in particular, please post your questions, okay? Check your understanding, with other students and with Gavin and I. Your questions may center on, oh, wait, is this what he is saying here, okay? Give your fellow students and Gavin and I an opportunity to, be a sounding board to make sure you are getting the main points and not getting, suffocated in detail that is not necessary for this class, okay? All right. And once again, so for this week, for this week, you will see the final 2 episodes. Is that right, Gavin?
That was for the Christmas lectures. That was last week. They watched the.
Okay, sorry. Yeah. So they will have seen all 5 already.
Yep.
Okay, but if you haven't, this is once again a plea to please take the time to watch these. I think it will help because one of the things that's nice about the Christmas lectures, the Growing Up in the Universe series, is that, first of all, these are aired on public television, on the BBC. They're designed to appeal to a mass audience. And so the pressure is really on Dawkins to get to the point. What is so important that you want to leave your viewers with? Okay, so it's another way of getting at, the crux of the matter. Yes, you will get some detail here and there, less so than I think in the book that we're reading. But it will give you another opportunity to appreciate what is the main point here. Why is Dawkins talking about these things? And it gives you another opportunity to get that main point. So please take the time to watch those videos, those lectures, if you have not already. For this week, and you can see it's moving along, we're asking you to watch the 3-part series narrated and produced also by Richard Dawkins, much more recently, called The Genius of Charles Darwin. Okay, it's a 3-part series that basically provides you with a really, I think, a very fair and interesting and engaging sort of overview of who Charles Darwin was, okay, why he is held in such scientific esteem, and what he is held in such scientific esteem for. So it gives you yet another opportunity to appreciate the importance of evolution, the importance of natural selection as the explanation for complex design. And in the context, you'll get plenty of examples, different set of examples from many, many different species, getting us to sort of the broader picture of what this class is about, that is animal behavior. So you'll hear a lot about Darwin, a lot about natural selection. Some of it you will have read about in this book, we will have talked about, but again, you'll get many different examples. Dawkins does some nice he does some interesting interviews with well-known people. Again, I think it gives you another context to try to, sort of grab a hold of this material. Okay, anything else we want to say, Gavin?
No, I think I'm all right.
So next week, then, we will finish Dawkins's book, and it's actually a slightly briefer section. It's chapters 8 through 10, so it is 3 chapters, and yet I think it's somewhat briefer in terms of the amount of material. I also think it's less less susceptible to getting lost in details. These last few chapters, these last 3 chapters, I think bring it back to the bigger picture issues. And so I think my experience with this class and with this book is that these last 3 chapters won't be quite as difficult or as taxing as the previous 3 chapters. But you, the students, I suppose, will be the judge of that. And we will look forward to talking more about that next week.
Right.
Okay. Shall we end it there then?
Yep. All right. Thanks.
Thank you.